Hello, everyone. Thanks for joining us at the ISTA 2019. And thanks for the organizers for the invite to be here on stage with you. So today, I'll be talking to you about teaching robots to program. And this talk will be more about why do we need to teach robots to program rather than how. I would love to talk about how, but it will take me at least a couple of days. So yeah, I'll try to focus on the concepts and why do we need to do that. So why should you spend the next 40 minutes listening to me talking about robots and programming? Well, I've been building robots since I was the age of 6, thinking about them, building, designing, programming. I was very lucky to end up at an amazing research facility to do my PhD at the University of Edinburgh, where I was in a lab with so many robots that the human-to-robot ratio was something like 1 to 5, and there were some peaks of 1 to 10. So we had many, many, many robots that we had to deal with. For the past 2.5 years, I was part of a UK startup called 5AI. It's currently the biggest, I think even European startup for autonomous vehicles, where when I joined, we were 15 people. We had a small demo. By the end of this August, we had a small fleet of around 30 vehicles roaming around London doing autonomous driving. We scaled from 15 to 150 people, raised more than $30 million funding. So we did quite a lot. But then at some point I realized I've spent my 10 years so far just doing the same thing. I look at some data, I have to figure out what sort of program I need to extract from the data to make robots actually do what I want it to do. So this is why very recently, as of last month, I started a whole new endeavor called Cyro Research, where what we really focus at is how can we teach robots to extract meaningful programs from raw data. And hopefully by the end of today, I will manage to convince you that this is really the next big blocker in front of AI in order to be applicable to any sort of technologies and societal problems we might have. So, technically speaking, I work at the field of robot learning and autonomous agents. And if I go to a party and people ask me, what do you do? I have two options. I can tell them I do artificial intelligence. And very often, we end up talking about Go and how we managed to beat the world champion in Go. I can also say I do robotics, and then very often we actually talk about this silly video of a $1 million robot not being able to do a very simple operation of turning a valve. Why is this? It's staggering, right? Something that, how many of you actually play Go in this room? All right, one person, two, amazing. Usually there's one at most. It's really hard problem. How many of you can turn valves? Right? Okay, good. So what's going on? Let's see. Well, Go is a very simple game in terms of representation, right? It's a board, it's a 2D array, you have some cells with the pieces of the one opponent, the pieces of the other opponent. The tricky bit in Go is planning and thinking. How do you actually play Go? So what happened with deep learning, especially a couple of years ago, DeepMind designed this really nice architecture where they allowed the neural network to augment a very standard tree search problem algorithm to play Go. So the way it works, you see here the huge search tree that the algorithm has to traverse, and where the neural network actually plugs in is exactly in these pink and blue rectangles, which says you don't have to play the whole game until the end to see what happens. We can actually train a network to predict how good a given state is. So this is what neural networks are really good at. They take some patterns, some input data, in this case the configuration of the board, and they tell you some numbers. It's a very concise, very well-defined problem. So this is what really made AlphaGo play much better than a human. It's the neural network combined with this search algorithm. So what are neural networks? Everybody's probably heard of them, used them somehow. So what are neural networks precisely? Well, precisely, there's one thing you should know about neural networks. They are the so-called universal function approximators. This means that if you take any function, however complicated, there is a neural network which can actually learn the function, given that you have enough compute time. And in terms of some very simple maths, here you can see very often y is our output, this is what we care about, x is our input, this is the data which we have, and we pass it through the network. The network has two key properties. The first one is the architecture, the sort of network that you'll be using. Convolutional network, recurrent network, and the other one is the parameters of the network. This is what we actually learned during training. Why do we hear about neural networks now, after a few decades of silence about neural networks and them being really uncool? Well, the first one is that we realized how to do neural networks on GPUs. And this allowed us to scale to huge networks that actually can solve interesting problems. Something we have to realize is also that typical nowadays neural networks, they have gigabytes of parameters. So nowadays, if you give me a GPU with 4 gigabytes or 8 gigabytes of RAM, I'll say that's not enough. Give me something nice like 64 or something like this, because we need to be able to fit everything in the GPU. And one of the key properties of neural networks is that they can compose. You can take one neural network and feed the output of the network into the next network, and you can stack them. And this is why they're called deep neural networks. And here you can see a diagram of one of the latest networks. You have 34-layer network, and this is something typical that we train on. Okay, so we won the game of Go, but it's very static. Can we do something better? Well, we did something better. A few years ago, again, DeepMind showed that you can train a neural network to play above human performance various Atari games. How did they do it? You have the network in the middle. On the left, you take input from pixels. So this is literally the image that the game provides you with. You put it through the network, and the network then says which is the best action to take in the current time step. And the results for this were this very interesting plot. So what you can see here on the y-axis, these are all the Atari games. And everything above the horizontal black line in the middle are games that the network actually learned to play better than humans. There are quite a few of them. What's more interesting, though, is one of the games at the bottom. There is a game called Montezuma's Revenge, for which the network did exactly 0%. This is a bit of an odd result. We have, with some cheating, been able to solve this game somehow, but with the vanilla setup, with the neural network trying to learn the game, it's not really possible. And later we'll see why. What else can neural networks do? They can do things which, actually, this is what got me excited about neural networks, is they can do things which I cannot. I'm a really bad painter. I cannot do painting. So if you tell a network, look, this is a nice image of Curiosity self-check from some day, I think in 2017. And on the right, I'll give you an image of the first impressionist art where you have the checkboard pattern being used as a motif. Then the network can provide you with something like this. Right? It's pretty interesting. I cannot do that. It's something, a whole new world is being opened in front of us. What else? You're like, okay, that's painting, playing games, not very useful. How many of you use Google Translate? I guess most of you, right? Well, I think since 2016 or 15, not sure exactly about the date, Google Translate started using neural translation. What they do is they have lots of corpora from different languages, and they've trained a network to take any language, map it to internal representation, and then they've trained another network to take this internal representation and map it to any other language that you want. That's why you can do all the pairs of languages in Google Translate. Very similar to things like LLVM. So that's quite interesting. How do those things look like? Well, it's not really complicated. It's just some sort of a neural network. In this case, it's a recurrent neural network. It has a few layers. Where Google really shines at is the fact that they can do this at huge scales. So you should not underestimate that. You can actually take the model. It's on archive. You can see the model from 2016. You can even get some data, but you're definitely not going to get the performance Google gives you with the Google Translate service. Right, so now this allows us to travel anywhere around the world and be able to at least understand some words that are crucial to not miss your plane or something. So what's next? This is a very recent data set, I think from 2 months ago, a month ago, so it's called face forensics. Do you see anything common with all those faces in this slide? Yeah, they look very similar, they say something. Well, the thing that you should care about is the fact that none of these people actually exist, and none of what they said, they actually said it. So this is all generated by a neural network that imagined some people generating something, some people saying something. This is why the whole data set is called face forensics, because now we are actually trying to understand when images are generated by networks and when they are genuine images. So it's getting really interesting. The next one is, for example, skill transfer. Ballet, something really hard, people devote their lives. PhD students typically cannot do it. But then you can synthesize videos of the PhD students being professional ballet dancers just by using neural networks. Okay, that's getting really, really interesting. One of the things to notice, though, is if you look closely at the generated video, there are some flickers here and there. So with all those visual tasks, what's happening is that your brain is really helping the network and actually synthesizing a consistent and valid image and valid video throughout the whole video. If you look at frame by frame, there are some weird things going on. So this actually brings me to, I think, the core of this lecture, and the core is, what are the limitations behind deep learning? We can do amazing things. Why don't we have personal robots? Why don't we have autonomous vehicles fully available everywhere for everyone? Why don't we have robotic doctors? I think I'm going to show you 3 things, which I believe are the core blockers, and then I'll show you how I think we can actually solve those things. So the first one, the very popular one, is generalization capabilities. If you train a network, then it most likely will not be able to generalize on any data that's out of your testing and training facility and training and testing data set. So if you put it in the real world, most likely it's going to break. You're like, okay, it's going to break, but maybe if you're careful about the data, if you're careful about the problem, we can solve it somehow and actually help it solve the problem. Let's consider the simplest possible data set, the simplest possible function that we would like to learn. That's the identity function, right? You take an X, you output an X. Everybody can do that, even neural networks to some extent. So in this plot, what you see is we train a neural network to essentially output the identity function on the range from -5 to 5. You can see the green shaded region. And all the curves that you see is the error for different activation functions ranging from -20 to +20. So you can see many of them in the training range between -5 and 5, they do amazingly well. But as long as you actually move from out from this region, from -5 to 5, you actually start getting error. So what happens is that the network hasn't really learned the identity function. It has somewhat memorized the data. And that's really a problem. It's really a problem if you think about real scenarios like autonomous driving. Why is it a problem? Well, if you show this to a network, it will tell you it's a stop sign. If you have a closer look, you'll see there is some spray painting on the stop sign. But this image was in our data set, so our network can easily recognize it. The problem is that we can generate lots of those images. In this case, we can just put some stickers. And if you put this sign through the network, you actually get a totally wrong answer. But I think for all of you, there should be no question that these two are stop signs. So the first problem is that we can generate those adversarial attacks. How many of you have heard the fact that Facebook has better than human state-of-the-art face recognition? Yeah, some of you. Well, Facebook has better than human face recognition. And this is what actually tags you when you upload your picture. Well, if you don't want to be tagged in any of Facebook pictures, just wear those glasses. And the thing is, we can design those glasses for any new algorithm Facebook comes up with, any new network they train. With some effort, we can actually come up with those glasses or any kind of clothing equipment on you or object in the image that will actually break the network. So this is a big problem. And this actually leads to a really deep fundamental problem about artificial intelligence, not just machine learning and deep learning, which is called the open world problem. I'll show you this video. This is what a Waymo car encountered one day traveling around Silicon Valley. This is a LiDAR scan. There is something in front of it. Try and think what this might be. Right? Google have driven millions and millions of miles. They've collected lots and lots of data. And one day, their car encounters a grandma on a motorized wheelchair chasing a duck in the middle of the street. There is no way you get all those corner cases in your data set. So you have to be smart about it. You have to have structure in what you're actually learning. So I hope I've convinced you about problems with generalization capabilities. The next one is interpretability and explainability. That's really, really a big problem. A few months ago, again, DeepMind, they released this amazing agent that managed to win the game of StarCraft against some of the top performing professional players. And I immediately went to their blog post. You can see it here at the bottom to the right, and read the blog post. I reread it. I reread it, and the only thing I kept thinking was about this. So in a nutshell, the more complicated deep networks get, they really become a pile of linear algebra and some fancy tricks here and there that we as scientists are not able to explain why do they exactly work. We are very engineering driven, very empirically driven, and yes, it might work, but we cannot put any guarantees on what the output would be and why would it work. Then this brings the question, would you trust such a pile of linear algebra that nobody really understands what's doing to drive you around? Trust me, it's really scary to be driven by a 2-ton vehicle that you have programmed yourself. It's even scarier if this vehicle has a huge black box that you've designed and it's in there. So this is one of the biggest challenges right now for autonomous driving, not only autonomous driving, but many, many areas where we really need some sort of machine learning, some sort of smart way of extracting meaningful data from the raw data that we get. Another example, can you trust a black box doctor? Very recently again, there was this very nice paper in Nature, the most prestigious, I think, scientific journal out there. And they said, yes, we've managed to train a neural network to perform better than trained doctors to detect skin cancer. Amazing. If you open the paper and you read carefully and you go to the supplementary material and you open the discussion, what went wrong, you can read things like, well, it happens that when doctors know that this is bad sort of formation, it's actually cancerous formation, they put a ruler on top of it in order to measure it. And it turns out that the network is more likely to predict cancer if it sees a ruler, not if it actually detects the cancerous formation. So there is this deep bias in your data that you don't realize it's even there. And neural networks are amazing at picking any correlations in your data, and they will pick it. And then at some point, you'll be wondering what is going on, because we as humans think in causal structure. Something happens, it causes some other event and some other event, whereas networks, they just memorize things. They see correlations, and this is what they learn. The last, I think, serious problem about deep learning is the amount of data and the computational resources we have to throw at it to make reasonably interesting problems actually solved. What you see here is a plot from, I think, last year, DeepMind again. They released an agent, reinforcement learning agent called Rainbow, and you can see the plot, the learning plot at the top for the Rainbow agent. So on the x-axis, you have how many million of frames the agent has seen. These are Atari game frames. And what sort of performance it has achieved. It's 100% means it's human level, above 100% is better than human level. And you can see that it takes 44 million frames for the agent to learn how to play. And if you transfer this into some tangible number for us, it's 17 days, 17 24-hour days, playing constantly, frame by frame by frame. I think I can explain to you how to play Pong or any of the games. It's probably 10 minutes, 15 minutes. So something we are missing there, and we have to figure out how to enable networks to actually exploit it. So yes, it takes a lot of data, but it also takes huge amounts of compute. And by huge, I mean staggering amounts of compute. This is, it went out, I think, somewhere in summer this year, a study of how expensive is it to train some state-of-the-art models for natural language processing. And the number that you should care about is the second to last line, the rightmost number. If you want to train the state-of-the-art network for natural language processing, with all the bells and whistles, it would cost you between 1 million and 3 million US dollars on cloud compute. You know, you can buy the servers, but it's probably going to be much more expensive. So this is a lot of money to throw at something that we've already seen that will break in very simple cases. So should we actually do that? Not only this, it's not only expensive, but it wastes humongous amounts of energy, as you can imagine. So this training wastes approximately, you can see here in this plot, 5 times the average emissions by a car lifetime in America. So they have big cars, and if you take 5 of them, their entire lifetime, this is how much CO2 emissions we make to actually train this model. And at the top of this plot, the top bar is actually a flight between New York and San Francisco, both ways, you know, just to put it in perspective. So we're wasting lots of energy. So all those things actually make deep learning and machine learning, the current state of art in machine learning, which is just a subset of artificial intelligence, hard to be put on any real applications. And robots is one of them. And this is what I care about. But this is for anything that has any impact on our society, be it credit scoring, anything that has impact. These problems are there, and we have to solve them somehow. So how can we solve them? Well, intrinsically, I do robotics and machine learning and so on, but at the end of the day, I program. And this is what I spend most of my time doing. And yes, very often I hear this. You said AI, I heard a few more if statements in my code base. Sometimes this is the case, sometimes it isn't. But then this should really make you think, okay, can we then figure out how to put this if statement automatically? Not hire a bunch of people, but figure out where this if statement should be and automatically bring it there. For me, this will be, again, some sort of machine learning, right? And the question and the answer to this is we've been trying to do this since the dawn of artificial intelligence. The reason artificial intelligence started, one of the reasons, it was a consequence of something called mathematics at the early 20th century, where we were really thinking about how can we do maths by doing maths, right? How can we derive theorems by thinking about theorems? And this led to the whole idea of, can we actually write programs that write programs? And one of the people, the co-founders of the whole field of AI, John McCarthy, he's the designer and the creator of the Lisp language, which is famous for being able to self-generate, which is crucial. So in those 2 slides, I'm going to teach you inductive program synthesis 101. At least I'm going to try and show you what the problems are and why is it useful. So this is an example. This is what inductive program synthesis means. You have some input data, you have some output data. You have to induce what program might actually lead to this relation. Any suggestions for this one? Yes, you just take the to the power of 2 to the power of n. And yes, that's true. It's a very simple function. It's very simple, but if you think deeply about what happened, is we've overcome all those 3 problems that I just mentioned. Now, this function, first, it generalizes to any n, right? If we've learned this function, it would work for any n. We've trained on n from 0 to 3, but now this will work everywhere. The next nice bit is that it's interpretable and it's explainable. I can take this function, I can analyze it, I can do static code checking, dynamic code checking, validation, verification, anything you wish I can do on this function, and I can guarantee what will happen if you run this function on any sort of data that you put in. And the last one is you need it only for examples. I'm not saying that it's easy, but you only need a few examples to generate that. So how can we actually leverage this and bring it into something that we can use? Another example. We can also generate sequences of data, not just some very simple function. We can generate lists of data. In this case, you might say, well, these are all the even numbers between 1 and 10. And yes, that's true. You can put this into an inductive program synthesis program, and it will probably spit something like this out, which is a very simple list comprehension. It puts all the numbers between 1 and 11 in this case, simply because of the way Python enumerates lists that are even. Great. If you're not careful about it, though, you can figure out other solutions, and your computer will figure out many, many, many other solutions. In fact, there is an infinite amount of solutions that will actually produce this. If you don't believe me, because you like this simple one so much, there is another one. You can take all the numbers between minus 100 and plus 100, and then just add one more condition that those numbers are between 0 and 11. Yeah, fine, maybe you can do some program transformation and simplify the second one to the first one. But then computers really can surprise us, and this is why we hate debugging, because computers are very surprising sometimes. Computers can do this. The computer can generate a program and it will tell you those numbers are the solution to the polynomial you see there. And they really are. The question is, did you actually want the computer to give you something that deals with polynomials, or did you want something to deal with the lists? The nice bit here is that we can control this. We can say what we care about, what we don't care about. Do we care about the ruler in the image? Don't we care about the ruler in the image? So we can very carefully control what sorts of relationships the computer can use in order to generate those programs for us. You're saying, okay, that's really nice, very nice mental exercises, but I'm going to go back to my daily programming. Well, you should think about it twice, because these sorts of technologies already exist in probably some of the things that you use nowadays. The most famous one, I think, by far, is the Google Flash Fill, the Excel's Flash Fill capability. If you just put one digit there and you drag it down, it will figure out what you want to do. And the way it's doing it, in the backstage, what's happening is that you have a computer, takes the data, it generates all sorts of possible programs that are valid with respect to what you've given, and it picks the simplest one. And you can drag and you just apply the program. So Excel, when you do this dragging, is actually doing inductive program synthesis for you without you probably realizing. Another example, which is, I guess, closer to developers and to software engineering, how many times have you had to spend days transferring one sort of data representation into other data representation such that you can use different APIs? Well, there are companies like Bylam nowadays who can actually consume those two sort of data sets, those two representations. You just have the initial thousands of lines database. It can tell you, give me the translation for those 5 lines, and I'll give you the source code that actually generates one from the other. And what you should note here is that the source data is in a language that the developer doesn't have to even understand. It just, in this case, is Japanese. And it also induces some relationships which are based on the semantics of this language that the developer doesn't understand. But we can do that, and it's actually something that you can probably use in your daily work. Okay, so we can do those things. What can't we do? What do I spend most of my time thinking about? I think about autonomous agents, robots in particular. This is Montezuma Revenge. This is the hardest game, the one that if you just train a deep neural network to play, it will give you a score of 0. It's a hard game because you have lots of entities around, you have this person moving around, you have to avoid the skull, use the ladder, take the key, then find the door. The stages also change entirely visually. But what would really help, and something that's beyond the capabilities of nowadays methods, is if we had this very simple program. If we possess the key, go find the door. If we don't possess the key, go find the key. Right? This is something very intuitive for you as a programmer. You know how to write those relationships. They're very simple for you. But deep learning struggles with this. So we have to figure out how can we augment the capabilities of deep learning with such very expressive programs. If you think about it, what I find remarkable about programming is that it's really the only language that we have expressed all the knowledge that we care about. Yes, we have those big books, we have all those maths books, but all the useful algorithms in those maths books are in some source somewhere actually being used. And this is the language that we use. We use programs to express all sorts of thinking that we want. And in fact, if we go a bit deeper, there is this whole notion, or there's this whole idea behind the so-called Turing-Church hypothesis, which says, yeah, human cognition is a symbolic operator that actually does execution of programs. And right now, it's a hypothesis because we cannot prove it, but importantly, we haven't disproven it. So how can we try and infer programs from data that we see? I'll show you one example. Unfortunately, I can't show you the things that I'm working on right now, but I'll show you some of the research that I've done which leads in this direction, and hopefully I'll give you an idea. So, program synthesis, one way to think about it is you just have to search the space of all possible programs. The catch is this space is infinite. It's really, really big. So you cannot simply search. So what you have to do is you have to figure out different heuristics of how to search this space faster. And some of the research that I've done is actually I've said, okay, you have neural networks that we can train for millions and millions of parameters, and we have programs that we can induce very simple programs. How can we combine the two? Well, I figured out that you can actually represent programs, especially functional programs, as computational graphs, which is what neural networks are, and then this allows you to optimize them before you search for the structure. So in this case here, you see some trace of a demonstration. This is what a person demonstrates to the computer or to the robot, stacking a bunch of cubes on top of each other. And this architecture, called the Pi machine, what it can do is it can actually find the program that solves this problem by first saying, I'm going to try the simplest program. I'm going to optimize as much as possible using deep learning techniques, something called, for example, gradient descent. Then I'm going to do some symbolic search, maybe A star or something else, and then I'm going to try and figure out the best program possible. Well, when I published this Pi machine, it was better than state of the art for many problems, and these are some of the things that we managed to do with it. So the Pi machine, we applied it to, for example, observing a pendulum wiggling around. And what the Pi machine induced, you can see at the top, the red number 1 is essentially the law F equals ma. And in this case, you see the gravitational constant 9.8. What's really interesting is, yes, we've learned this number, but we've learned a relationship that's valid for any sort of system that we now care about. This is what Newton did, I don't know how many centuries ago, and this is what we can now do and apply to any sort of system that we care about. You can do the same thing for even more complicated systems. You can do the same trick to actually try and explain neural networks. I said neural networks are big black boxes. We have no idea what they do. You really don't want to be driven by a big network taking decisions for you, especially when there are grannies or scooters chasing ducks around. So you can take this, you can train a network to play the Pong game, for example, and you can see the trace that the network generates, essentially see how it plays, and then you can pass this trace, this data, to the Pi machine, and it will output something. And this something in this case, if you look at number 2, it's a candidate program, which essentially says, yeah, the network actually prefers to move in a direction that's proportional to the difference between the agent Y position and the ball Y position. And this is something very intuitive you as a programmer would write down. This is called proportional control. And if you look at the top, there is a slight twist because you can add different coefficients because the environment itself has some friction. Now this program, 3 lines of code, maybe even 2, depending on how you format it, can actually replace the, I don't know, 2-3 gigabytes of parameters that the network was. And the sort of performance we get, the human does 9.3, the DQN is doing 18.9, the program, the 3 lines program, is doing 11.1. It's not as good as the network, that's true, but it's still better than human. And for many applications, what we care about is only being better than human. We don't want to be the most perfect agent out there. What else? If you apply the Pi machine again to the problem of the tower building, it can use a program like this. The interesting bit about this program is that it has figured out, there is one variable that I should care about. I'm going to actually allocate it on the stack. And I'm going to pass this variable to function calls of addition with all sorts of other things. And if you try and understand what's going on, we've actually induced the relation above. We've induced this relation, and now this relation above, from a single demonstration, we know it, and it will hold regardless of what sort of task, where you want to solve it, what robot you have to solve it. This is the intrinsic semantic knowledge in the data that we really, really care about, and this is what we as programmers spend most of our days trying to extract from the specification of the problem we try to solve. Another example, this is very recent research. It got published this year at one of the most prestigious conferences on machine learning called ICLR, International Conferences on Learning Representations. And what this work actually is doing is, I think, closing the loop. We see how networks are amazing at perceiving and using raw data to actually output something, but they're not very stable. We also have programs which are extremely robust to all sorts of noise in the input data. They really capture the semantic of what we want to express. So this work actually showed how we can combine both. Here you see a very simple Minecraft-like environment where the agent has to navigate around. And what we did, we said, we'll have a convolutional neural network to process the images. They're really the best tool we have so far. But we're going to feed the output of the network into the program directly. And in this case, the program is, I've literally downloaded the Python A* implementation, and I said, I want this network to learn to use this package. And if you train this, you can actually get the network to learn what you want it to learn and actually use this program correctly. What's more interesting is that programs, they are semantic beasts. They give you lots of semantic knowledge. And by putting programs on top of your networks, you actually force them to learn semantics. And this is without you doing any sort of labeling. If you've been using deep learning for anything, you know that labeling is one of the hugest costs you have to pay. So by putting programs on top of networks, you can actually train networks to do things you want without you spending the effort of labeling lots and lots of data. Okay, that's interesting. How about something in the real world, as in a real physical robot with real physical noise and all the things that come with physical systems? Well, there is one very fundamental problem, again, in AI, called the physical symbol grounding problem. And what it stands for is, let's say you've seen the task that we can learn the program for, how to stack cubes. And we want to tell the robot, build me this tower, right? We can specify this somehow. We can even figure out this program, right? We can do planning to generate the program. We can do the Pi machine to generate the program. The problem is that the program or any specification we provide will be in terms of those variables. For example, the variable red cube. What is a red cube? For you, as a person, you know very well what a red cube is. For the robot, it's just some array of two symbols that it doesn't know what they are. What the robot knows, it knows pixels. The question is, how do you map those variables to pixels? And some of the work that we've also done is we can actually align raw data with programs to actually extract exactly what each symbol means in the data. So now the robot knows what you mean by you saying red cube or yellow cube or build me a tower of those 5 cubes. We have visual pixel representations that the robot can actually understand. And if you run it, yeah, now the robot has learned all the symbols. It has the programmatic structure, it's learned all the symbols, so now it can solve the task regardless of how the cubes are placed, where they're placed. I can even change the goal. I can even change, say, a different tower, but because we can do the planning, we can even solve this task. So now from a few demonstrations of how to do it, we can extract all this, and now we can automate lots and lots of things. And I think the last and most interesting one is probably, now that you have this programmatic structure, and you know what people are doing, you can actually start assisting people. So here you'll see me building a robot with another robot. I told you we had too many robots. So I'm building this robot called the Cookabot, the U-bot, with the Baxter, the red robot, helping me without me saying anything. I'm just building whatever I'm supposed to build. I wear a very interesting sensor, which is eye tracking glasses, which gives some more information to the robot, but then the robot actually processes the sort of programmatic structure I have for the task. And it also knows that the programmatic structure. It's a few steps, you can do some changes, swaps around, but eventually just a program. And the robot can do inference in real time, what sort of program you're executing as a person. It can actually assist you without you saying a single word, which, as you can imagine, is very, very useful in different industries. One of them is, for example, pharmaceutical industries and chemistry, where they have workers roaming around warehouses endlessly to just get different sorts of solutions. Well, we can automate this now. You can have the worker working on whatever they're supposed to do without you wasting a single % of their cognitive load and assisting them to solve what you need to be solved. So I've shown you all those things, and I want to finish with some personal message to you guys. So I've moved back to Sofia 2 months ago because I think there is huge potential for Sofia and Bulgaria to become the next big player, a very big player at the international stage for artificial intelligence. I know that the one thing missing is the know-how in terms of AI. And that's why me and my team, what we try to starting from next year, probably early spring, is a masterclass, a long-term masterclass targeted especially to developers, people who know how to program, but lack the know-how in terms of maths and AI. So if you're interested, and if you want to join and learn about technologies that are really going to change the world, you just go there, subscribe, and we will invite you to apply. And I think that's me. Thank you very much.